Elliptic curve cryptography or CCE. What is ECC? Elliptic curve cryptography or ECC has existed since the mid-1980s, but it is still looked on as the newcomer in the world of SSL and has only begun to gain adoption in the past few years. ECC is a fundamentally different mathematical approach to encryption than the vulnerable RSA algorithm. An elliptic curve is an algebraic function y2 equals x3 plus ax plus b, which looks like a symmetrical curve parallel to the x-axis when plotted. As with other forms of public key cryptography, ECC is based on a one-way property in which it is easy to perform a calculation but infeasible to reverse or invert the results of the calculation to find the original numbers. ECC uses different mathematical operations than RSA to achieve this property. The easiest way to explain this math is for an elliptic curve. A line will only pass through 3 points along the curve, P, Q, and R. And that by knowing two of the points, P and Q, the other R can be calculated easily. But with just R, the other two, P and Q, cannot be derived. ECC is used in both digital signatures.
Singular elliptic curve. If for a to raise to 3 plus 27b raised to 2 is equal 0, then we have a singular elliptic curve. This could potentially lead to, to having three distinct roots. Therefore, we must deal with non-singular elliptic curve with the condition for a raised to 3 plus 27b raised to 2 is not equal 0 in order to assure that we have three distinct roots. This will allow us to establish the fact that the solution set E elements symbol form an abelian group. What is a group? Suppose we have any binary operations such as additional plus in open parentheses that is defined for every element in a set G, which is denoted close in open parentheses and G and plus signs. Then G is a group with respect to addition if the following condition holds. Number 1 is G is the closest under additions X and elements symbols and G symbols and Y and E elements symbols and G. Implied X plus Y, E element symbol and G element symbol. Number 2, plus symbols is associative for all X, Y, Z and E element symbol and G. And X plus and close in open parentheses Y plus Z equals Y plus Y and plus Z. Number 3, G has an identity elements E. There is an E in G such that X plus E equals E plus X equals X. For all is X and elements symbol and G. 4 is G contains inverses. For each X and E elements and G, there exists Y and E elements symbols and G such that X plus Y is equal Y and plus X is equal E symbols. Y plus X. Next is ECC operations. Given a curve E defined along some equation in a finite fields such as E symbols and Y and y2 plus x3 plus ax plus b. Points multiplication is defined as the repeated additions of a points along that curve. Denote as n p plus p plus p plus p, etc., etc., and plus p for some scalar integer and a point p equals x and y open and close parenthesis that lies on the curve E. This type of curves is known as a Weierstrass curve. The security of model ECC depend on the intractability of determining n from Q equals np. Given known value of x and p is n is large, known as the elliptic curve discrete logarithm problem by analogy to other cryptographic systems is multiplicity. Given 2 points on E elements, say P and Q, let R be the third points of intersection of P, Q, and E. The P not plus Q is the third point of intersection of O and E elements are vertical lines through R and E. Next is point operation. Point and infinity. Point of infinity is the identity element of elliptic curve arithmetics. Adding it to any points result in that other points, including adding points at infinity to itself. That is 0 plus 0 is equal 0. 0 plus p is equal p. Point of infinity is also right as 0. Next is point operation. Point negotiation. Point negotiation is finding such a point that adding it to itself will result in point of infinity. P plus negative p is equal 0. For elliptic curve that is a point with the same x coordinate but
Point operations. Assuming the elliptic curve is given by y2 equals x3 plus ax plus b. This can be calculated as t equals ya negative yp over xa negative p xr negative t raised to 2 negative xp negative xa. Yr equals t xp negative xr negative yp. These equations are correct when neither point is the point of the infinity 0 and if the points have different x coordinates, they not mutual inverse. This is important for the ECDSA verification algorithm, where the hash value could be 0. With two distinct points, P and Q, addition is defined as the negation of the point resulting from the intersection of the curve E and the straight line defined by the points P and Q giving the point. Example: P plus Q equals R, XP YP plus XQ YQ equals XR, YR. Three cases, four solutions. Suppose P, Q belong to E, where P is equal X1, Y1, and Q equals X2, Y2. We must consider three cases. Number 1, X1 not equal to X2. Number 2, X1 equals X2 and Y1 equals negative Y2. Number 3, X1 equals X2 and Y1 equals Y2. These cases must be considered when defining addition for our solution set. Defining addition on E case 1. For the case X1 does not equal X2, addition is defined as follows. Example, X1, Y1 plus X2, Y2 equals X3, Y3 belongs E where X3 equals Y2 negative X1 negative X2. X3 equals Y X1 negative X3 negative Y1 and Y equals Y2 negative Y1 slash X2 negative X1. Defining addition on E case 2. For the case X1 equals X2 and Y1 equals negative X2. Addition is defined as follows. Example, X1, Y1 plus X2, Y2 equals X3, Y3 belongs to E where XY plus X negative Y equals 0. The point at infinity